Hey everybody, welcome to our webinar today, Geothermal Heat Pumps, the most efficient heating and cooling. I'm Joe Archunas from Electrify Now, here as always with my teammate Brian Stewart. And we'll introduce our panelists in just a second, but really happy to have you with us here today to talk about this really important topic. And as a reminder, this webinar is part of our, I wanted to also say this webinar is brought to you by Electrify Now. We are an all-volunteer all electrification program. We advocate for electrification as the quickest path to decarbonization, as well as San Diego Learn. San Diego Learn does a lot of webinars on and education on electrification topics. We'll put their website in the chat, but check them out. And this webinar is brought to you as part of our Go Electric Benefits for Homeowners webinar series. We believe that electrification is a key to lower energy bills, cleaner indoor air, less pollution outside, more comfort in your home, and increased safety. So Brian, today we're talking about geothermal heat. Talk to us a little bit about this.
Yeah, thanks, Joe. So this is a topic that seems to be getting more and more energy and excitement around it all the time. And just to kind of maybe level set a little bit before we get into the details, there's multiple ways that you can get heat and energy out of the ground. And one of the ones that's been around maybe for the longest and is most thoroughly developed is what we would call geothermal heat pumps that are usually in applications for single buildings, residential or commercial. So that's a common one, but you're also starting to hear more about thermal energy networks now, which is basically a larger version of the same thing where many buildings are attached to the same system, larger system. And there's other benefits from this because different buildings have different energy requirements. In some cases, they can be helping each other to heat or cool, which is exciting. And that's something that's gaining a lot of momentum, but still relatively new as a applied technology. And then another one is geothermal electricity generation, which is very exciting because it's potentially a way to tap into hot rocks or hot sources of water that are deeper under the ground to generate electricity for firm energy generation that's 100% renewable and carbon free. So these are the three sort of big buckets of geothermal energy that you hear about. Today, we're really going to be focused on residential geothermal heat pumps, but of course, everything we're talking about today could be applied to small commercial buildings as well. And we've got some great panelists to talk about that in just a minute. So today what we're going to be doing is we're going to generally be talking about how geothermal heat pumps work, what they are, what their benefits are, and their benefits are multitude. It's not just to owners of the buildings. There's other benefits we'll be discussing. We'll be talking about why it might make sense to invest in a geothermal versus an air source heat pump. These are both two great technologies that we're never going to try to denigrate either one of them, but they do have different applications. We'll try to tease that out today. And then we're going to talk, practically about generally what are the costs to install and what would you expect from operating costs from a geothermal heat pump. And of course, incentives is a hot topic. There's some really good ones available. They vary from state to state, so we'll cover that a little bit. And then I think finally, what we hope you walk away with today is just a better idea about whether your property is a good candidate for a geothermal heat pump, or maybe what are the situations where geothermal really shines. So we have got two really fantastic panelists with us today. We've got John Chiovacco. He's president of Aztec Geothermal based in Albany, New York. Aztec is a heat pump system design and installation company focused on geothermal applications for residential and commercial buildings. They do thermal energy networks. We'll touch on that, of course, but we're not going to go deep on that today. We'll probably have to do a whole separate webinar on that topic. But John is also a board member of New York Geothermal organization, which is a nonprofit group supporting the geothermal industry. And he's got all the right degrees in mechanical engineering from Union College, as well as all the engineering accreditations you would want for geothermal systems design, installation, and inspection. And we're excited about having John here, partly because New York is kind of a hotbed for geothermal. We've also got with us Nick Cabianca from Geonomic Developments. That's a Portland-based organization, and they work on the West Coast here, Oregon, California, and Washington. Nick's the co-founder and general manager of Geonomic, and their firm specializes in geothermal heating and cooling systems across the Pacific Northwest. He also serves as a member of the board of directors for Northwest Geo Exchange, which is kind of similar to the New York Geothermal organization that I mentioned that John's part of. It's a nonprofit that supports geothermal in the West Coast here. He's a certified geothermal inspector and licensed contractor, and he spent his whole career focused on sustainable construction and renewable technologies. So I think between the two of these, we get a really good picture of two different regional takes on geothermal, and a lot of experience between these two on applying this technology to buildings, commercial and residential. So welcome, Nick and John. Thank you for being with us today. And maybe as we tee up the slides here, you might just fill in any part of your bio or your experience that you think that our audience might want to know that I didn't cover in that brief introduction.
I'll jump in, and then we'll go to Nick, and then Nick will get rolling with the slides. So John Shabako, Aztec Geothermal. Thanks so much, Brian and Joe. And this webinar series just is terrific. Great to be a part of it, and great to have so much attendance too. Well promoted. One of the things is that a lot of our industry has come up through doing smaller projects. And that's a lot of what we'll talk about today. My company out in the upstate New York area and parts of Massachusetts have done over 650 single family homes. Most of those, I would say about half new and about half existing homes. So there's lots of retrofit opportunities. So it's not something just for new construction. And there's not one size that fits all as we go through this. So there's lots of flexibility with how we connect to the ground and then how we implement that in a house. And so looking forward to talking with you and exchanging information with Nick.
Yeah, I'm Nick Cabianco with Geonomic here in Portland and the Northwest Geo Exchange. And yeah, thanks again to Electrify now for allowing us to talk about it. It's been around for a while, as we'll kind of get into, but there's been a lot of interest, especially in the last 4 or 5 years, towards geothermal systems. And we'll get kind of into why that is here in a little bit.
Hey, can I just say too, as you guys get going, I think we've got to say this, if you in the audience have questions that you want to put in the Q&A, that's our easiest way of tracking what it is you're interested to make sure we're covered. We'll be monitoring that. It's harder for us to monitor the chat. So if you got a specific question, please put it in the Q&A.
Yeah, I guess sort of to start. I mean, there's a lot to cover. There's a lot of angles going on right now with geothermal, but I mean, as a starting point, I think it's a great thing to start with. Why should you be interested in geothermal? Why should you be interested in learning more about geothermal, and possibly finding out if it's a good fit for your property or for your project? There's a lot of different ways to say why, but ultimately what we're talking about is sort of the best way to do heating and air conditioning. Heating, AC, hot water is going to be the largest energy use in residential applications and some commercial applications as well. But that's really kind of as a starting point. I think that's why people should take interest in geothermal. It's been studied kind of across the board by every agency out there. And it's been proven to be the most energy efficient, the most sustainable, and the longest lasting.
So one of the things that comes up a lot is that it seems like it's a new technology, or it's and this is just a slide that I took from somebody else a while ago, and actually I found the magazine recently. I was able to purchase it, but this is from 1948 from Life magazine, and one of the features in it shows that the Miracula, which is a kind of a monster of a heat pump, but it's a water source heat pump, a geothermal heat pump, and it still has the same basic components that we have in heat pumps today. Really, geothermal in some form or fashion has been around since the start of refrigeration. So the air source systems sort of mimic what a refrigerator inside your house does, and a ground source system is taking that thermal energy and exchanging with the ground. So next slide. Even though it looks like the next slide is really eager.
I know it seems to be on like a roll. I don't know. Yeah.
Keeps trying to pop in. There's 2 big studies that came out that the DOE did for the industry. or as a part of what they thought would be good for the country. One of them that Oak Ridge National Labs took a lead on is off to the left here, and it came out at the end of 2023. And it's kind of a grid impact study or an impact of geothermal heat pumps. It assumed that 70% of all buildings would convert to geothermal, and what would those impacts be? And it showed that there were tremendous reductions in the need to build out a larger grid. So there's tremendous avoided cost related to that. And so they basically are saying that if we electrify buildings with ground source heat pumps on a broad scale, then we don't take down the electric grid, or we don't stress it or have to make nearly the investments in it. Obviously, heating and cooling and electrifying buildings is part of what's going on, but if we just draw a circle around that, that's good. The other study that came out more recently, just in January of this year, says if it's a good thing based on the original study, how do we commercialize it? And those are pathways studies or liftoff studies that the DOE puts out. And those should be links. When we get this, you'll see that there's a link up right now because they're cursored over it to try to keep the slide from moving. So those studies are both recent and really very positive to say that this is a technology that should be taken seriously in the United States. Next slide.
Yeah, and different types of heat pumps. I mean, they kind of touched on earlier. When we meet with clients, a lot of times, one of the initial questions we get is, how do these systems work? And for a lot of people, the easiest way to explain it is through a system that they're more familiar with. So Geo heat pump is going to work in a very similar manner to an air source heat pump. One of the ones we use as an example is, just a classic refrigerator. If you put your hand on the back of that refrigerator, you're going to feel warmth, and that's from the refrigerator exchanging that heat with the air next to the refrigerator. So, in cooling, what you're doing is you're taking heat from within the home and you're dispersing that heat. And then heating, what you're doing is you're pulling heat either from the air or, in geothermal heat pump case, from the ground. I'll go to the next one. Yeah. And this is just another example. One of the things that, geothermal sometimes is thought of as like John sort of touched on, as sort of a new or a different sort of technology. But what we think makes it most practical in a lot of ways is that it is, in a retrofit situation, it is going to be replacing something you already own. So you're not adding a new piece of infrastructure. It's not a new system, if you will. It really is just serving as something that most customers already have in their home.
And if we think about the underpinnings of the technology, a lot of the energy is really the modulation of the Earth's temperature to keep the ground at a constant temperature. And so we access thermal energy. The map keeps trying to jump in there. So if you go to the next slide,
Sorry about
you
that.
could just right click on it. It probably will hold its position for you.
Let me see here. Let's see.
If we go to about really 20, 30, this particular is 30 to 60 feet below, we get a pretty constant temperature in regions, but that temperature is a little different. It's impacted by weather and also by the sun warming the earth. And you'll see that in the area that we are in New York, we're more in the sort of 50, high 40s. If we get into dense urban environments, maybe 56. But if we're sort of the cave temperature, if you were in a cave in those areas, that would be the temperature of that cave. But that would say if we're in a cave in Miami, Florida, it would be 77. So these are like starting temperatures as the thermal source and sink for energy for a geothermal system. And as a result, we get somewhat different performance in different regions, but it's all pretty much in the same zone for most of the United States. Next slide. These are some of the different ways to connect horizontal systems, very idealized pond systems where we might drop plastic pipe in a closed loop in a pond. We could extract energy right from the pond and bring it in, but it's more common to have a closed loop system where we're using those pipes as an energy transfer mechanism. Vertical ground loops are probably the most common. You may or may not be able to see me, but we've got polyethylene pipe, and then we drill like we do for a water well, but then we put a pipe down there and we circulate water in that closed loop and bring it to the heat pump. There's also direct exchange, less common, but is used in some places where actually the refrigerant from the heat pump makes a direct exchange with the ground. And those are copper pipes, and they often go down in that sort of inverted pyramid shape. So they have a smaller footprint. There's some advantages and disadvantages really to all these systems. And for the most part, when we look at a building, we look at a home, we think about what's the best for that. Vertical ground loops tend to be favored in areas that we have rock relatively close to grade, and we don't have a whole lot of land to work with. Horizontal systems can work well, especially like in new construction, where you're already doing a lot of site work. Maybe you're just going to bury those pipes maybe 4 to 6 feet, depending on the area that you're in. Pond loops, not everybody has a pond, and that pond really has to be under your control. So it isn't something, it's really quite difficult to do that where there's a shared pond resource. It's hard to get everybody to agree that that's going to be a good thing. Next slide.
And this is just some other examples of, how do these systems go in, and what does that really look like? It's one of the kind of challenges sometimes in putting proposals even together is, what would this look like actually going into the ground? So the picture on the left here is what John was describing as a horizontal or a trench system. So in this case, these are, if I remember right, this was 200 foot in length. And basically you're going to put piping at the bottom of this trench about 6 feet deep. And that's going to serve as your ground heat exchange system. In the right hand side picture, that's a picture of a vertical drilled installation in progress. So it's going to serve in the same way, but instead of those long, linear trenches that that borehole in this instance was 400 feet deep. And you're going straight down into the ground. It's a small diameter borehole. That's something that surprises people a lot of times. In this case, it was a 6-inch bore that went down about 400 feet. And then, like John said, there's a lot of different ways to do it as well, depending on the site and depending on the specifics.
Nick, that's a little surprising that in the horizontal it's only 6 feet deep. Is that common that it's just that shallow in the ground, or do you go deeper?
It is. I mean, someplace, Minnesota, Alaska, you're going to need to go deeper. But in Pacific Northwest, you get down to about 5-6 feet is where you're going to reach that pocket of constant temperature. And you don't need to go deeper. We say the ground becomes more consistent the deeper you go. But you're going to see a very small temperature change between summer and winter down at only 6 feet deep.
Yeah, the seasonal temperature change that you might see at 6 feet is accounted for by having more surface area. So you'll generally have more pipe in a horizontal system than a vertical system to accomplish the same thing. But if you have enough room and excavation is cheap, or you're doing a lot of site work anyway, it can be the lowest cost. And both of those systems can operate very efficiently. Both.
Hey, while we're on this, I mean, is there a big difference in cost between these two techniques, or is that impossible to say because it's so site specific?
Oh, I mean, it most often is going to be less expensive to do a horizontal trench system because you're typically using just a standard excavator. A lot of times we'll work with, like in new construction, with the grading contractor or whoever's doing site work. They're already going to have the machine there. On the vertical, and I'd love John's answer as well on the vertical out in New York, but depending on where you are, vertical drilling can be not just more expensive, it can be significantly more expensive.
Yeah, I would say in our market too, in the Northeast, the verticals are generally more expensive, but we have a lot of dense urban environments or even suburban environments where you don't necessarily have the room. And also maybe someone has a very manicured lawn or some kind of other features that they don't want disturbed, because the area that the horizontal takes up is considerably larger. So it's really site specific. So it's good to have a few different arrows in your quiver.
And then this slide covers that piece of piping that John pulled out. A lot of times people ask, what is doing, what are you pumping the water through to do the heat exchange? And it's HDPE. The upside to HDPE is it's extremely durable. You can get, depending on the manufacturer, it can be a 50-year warranty on the piping system. It's sort of, in a way, hits the sweet spot of kind of cost and thermal conductivity. It is the durability is really what you're after. We say when these systems are installed, fused, tested, they really should be able to serve multiple heat pumps through their life, and last, depending on who you ask, it could be 100+ years.
Yeah, I don't know, Nick, if you're getting into this later, but the idea of like, do you avoid putting plants over them to increase that durability?
Typically, we've done systems in Oregon where there's, commercial productive farm on top. Most root systems aren't going to go down even 6 feet. So typically it's not an issue at all. You kind of maybe want to account for your long-term plan, depending on what you want to do. But most root systems aren't going to be anywhere near where the piping systems can actually sit.
Okay.
So we'll talk a little bit about how the systems work. This is not a refrigeration course, but we've talked about this closed loop system where circulating water, usually in northern climates with a little bit of antifreeze in there. And it isn't so much that it's exposed to outside air and might freeze. It's just the heat pump will extract thermal energy from the ground and over the course of the winter will depress in temperature to the point where you can approach freezing, and it still can operate very efficiently there. So that makes an exchange with refrigerant inside the heat pump in most cases, and then the compressor is used to basically make that refrigerant up to temperature by compressing it. So that closed loop of water creates a gas in the evaporator. That gas then is compressed by the compressor, taking electricity, and then that is what is used to heat the house into that heat exchanger with the air. That system is also, next slide, reversible. So the water is always moving in the same direction in the ground loop, but inside the heat pump itself, it actually reverses. And this is a slide that Water Furnace put out a long time ago and lots of us use. And it just shows you that that basically we're pulling energy from the loop in that heating mode. Energy is being absorbed by the water. And then in cooling mode, we're absorbing energy from the house and we're dissipating that heat into the ground. And in most residential systems, there's enough time between seasons where those would balance back out to that sort of mean ground temperature or undisturbed ground temperature. In larger commercial systems, that balance between summer and winter heating and cooling is very important because it acts more like a thermal battery, and it'll tend to drift cold or drift hot depending on the energy balance from that building. Next slide. In our climate and in existing buildings, we oftentimes have high temperature distribution systems. So we'll have a boiler system, and then I'll send it to hot water baseboard, and you'll see the explosion of that little single fin. And you need to have pretty warm temperatures, say 160, 180, to make that room warm with that type of technology. Steam is obviously going to be at a higher temperature, hot water radiators. Also, existing systems sometimes have central ductwork. They might have a furnace or a furnace with air conditioning. So that's kind of what we come across. Next slide. Heat pumps don't make as hot a temperature as boilers. Certainly, they start to lose efficiency as they start to get anywhere near those temperatures. So we use more surface area. And if we only needed to heat, we might just increase it with a bigger radiant panel or a high efficiency baseboard with more surface area, or radiant floors can work really well with this technology delivered as water. So you have a heat pump that makes the water. But if we want cooling too, a lot of times we want to use something like that ductless high wall unit, maybe a console unit, a fan coil type unit that could have that either water or refrigerant in there that's hot, and then we blow in hot air, but then it could reverse. We could put cold water through that coil or cold refrigerant through that coil. Ductwork is pretty easily adaptable. Sometimes the ductwork for an existing system isn't sized properly for the heat pump, so we might need to make some adjustments. But basically, We have, I would say, the majority of the homes that we convert, we actually put in central ductwork or a couple of ductwork systems. Sometimes we do a ductless approach, if that seems to make sense.
John,
Next
so
slide.
on this slide, maybe before you go on, so I just wanted to dwell on this for a minute because in the Northeast, you know, boilers are a big thing. So these radiant systems, like you were talking about, are really common. Here on the West Coast, that's less of a thing. Here, you probably have electric baseboard or some kind of gas hot air furnace is the situation. So I think what I'm taking away from this is if your home has good ductwork already, then like if you had a gas furnace, for example, it would be probably pretty straightforward conversion to an air-based system to heat and cool.
That's right.
But if you don't have good ducts, then you might have to either put in better ducts or use some of these other devices in order to get the heat dispersed. Is that a good way of?
That's correct. And if you want cooling, you'll need something that has, you know, a fan coil, something that blows air over either a hot or a cold coil. And that if it's what's nice is that since we need more surface area to heat a building with heat pump water, if we use water, that same surface area is the kind of surface area you need for cooling anyway. So the technology works very well in some of those other, say, that ductless high wall unit. If you go to the next slide, I'll show you kind of a lot of different variation as you get to a refrigerant distribution. There aren't too many products that serve this, but this is maybe the most variety that you can have, because we could go with a high wall unit, or we could go with air handlers and put ductwork on those air handlers, or that console unit that's towards the bottom. And then you can have multiple of those attached to a single compressor unit. And that single compressor unit, in this case, is connected to the ground loop. So these are water source, sometimes called water source variable refrigerant flow systems. I wouldn't say that they're super common. And now with refrigerants being regulated and changing, we take these seriously. We don't do this unless there's really a need. And this meets a special purpose, but this gives you probably the most flexibility in terms of the conversion. Next slide. We just happen to have, this is with 2 air handlers. So that's one of those systems. And you'll see the black piping that's connected over to the left side of this slide to that Samsung unit. Those are the water source pipes that come in, and that's from the ground loop. And then there's refrigerant piping, and they're copper pipes. They're not insulated yet, but they're copper pipes right above that. And those go to 2 air handlers, one in the basement and one in the attic. And then there's ductwork systems in the basement and the attic that go off that single compressor unit. That same technology works in an air source unit. You can imagine that unit, if it was air source, would be outside, and it would then go, say, to those 2 air handlers or a number of ductless units. But there's lots of flexibility in terms of how we can convert homes. Next slide.
And I think the next few slides are just sort of some example or some more example pics of, you know, what would this look like within a home. These happy clients here, this is actually something that's really popular in our territory, and it's called a dual fuel geothermal system. So this system is actually, the client previously had a natural gas system, and this the geo system is fixed with the natural gas system. There's some different reasons to do that. Some of it has to do with generator backups, and you can go down a whole wormhole as to why someone may want to do a dual fuel system, but it is an option. Some people like as that backup instead of electric resistance or something like that to keep their existing gas infrastructure. So you see in between the 2 clients, that white box is the geothermal system, and then to the right is your more traditional gas furnace. And then this picture on the right is what we would call a packaged geo heat pump. So everything's going to be in one box. So this black part on the edge there, that's going to be the flow center, which is going to be pumping water between the ground and the unit. And then that unit itself is going to essentially do everything. Heating, cooling, and in this case, domestic hot water preheat as well.
Hey, Nick,
and we can go to
quick question on these. Is the gas or electric resistance backup used during just in emergencies when the power is out, or in extremely like cold weather where the geothermal couldn't keep up?
There's a couple ways to approach it. We're typically gonna design the ground heat exchanger for 100% capacity. So we're gonna design it to cover the full load. We'll often recommend a backup heat, and it's just kind of like you said, Joe, for true emergencies. Sometimes it could even be, service. Depending on the temperature outside, it can be a mechanism to keep heat on, just sort of no matter what. The interesting thing when you get into, natural gas systems, we hear it all the time. And when the power goes out, you're still not going to have a furnace, because that fan's going to run on electricity. And then, Joe, what was the second part of your question?
I think you covered it.
Okay.
Cold and just the emergency backup. Yeah.
Yeah. So we're not typically going to design for it to cut out at a certain temperature outside and go to backup heat. We're going to design them as a true emergency backup system.
Okay. So they're using geothermal most of the time, and then it's just this emergency backup. Got it.
Yep.
Nick, another question just on this packaged system on the right. I was wondering about that because it feels like the geothermal systems that I've seen, some of them, they all seem so bespoke, like each one is slightly different combination of units and stuff. Is there kind of any kind of trend towards this more like, one box you stick in that's got everything in it kind of thing that's already got all the components you need? Or is that what you're showing here?
That would be what we call a package system. So it'd all be in one box. So even, we call it the superheater, domestic hot water preheat. That's all built in, secondary heat exchanger inside the box. The reasons to go to a split system, there's a lot of sort of use cases for why someone might want to do that. The sort of drawback, if you will, to package systems is you're going to need to utilize electric resistance as that emergency backup. You're not using the emergency system. It's there in case of an emergency, but what that requires often is a pretty large electrical circuit. So sometimes, depending on the panel in a residential application, they might not have enough capacity to add an electric resistance backup heat system, if that makes sense. So they may steer towards a split system just for that reason. There's a lot of nuance, just sort of depending on the use case, but those are typically going to be the driving factors towards someone not doing a package system. Is going to be, for whatever reason, they want to maintain and utilize the gas system as their backup, or they just simply don't have the total capacity for electric resistance backup.
Thanks. That's helpful.
And this is just more of the same. So this picture on the right is example of a split system. So I picked this picture because it shows you don't need, the system doesn't need to be right next to the air handler. It can be sort of remote, if you will. And they're relatively small boxes. We're talking the size of a, small mini fridge, something like that. And then this system on the right is going to be another example of a package system, but a sort of a smaller and different duct setup there. And then this slide is showing a radiant heat system. And so one of the things where geothermal really shines is in hydronic heating. And you can use hydronics in a lot of different ways. You can feed air handlers, do forced air. What we do a lot of here is in-floor radiant heat systems. And this is an example of this.
Seems a lot more complex than the furnace, the air handler setup.
It is. There's more pieces, certainly. We're running, tons of tubing through slab, and and then there's the whole control side of things that go along with it. But the guts of the system is really going to be the silver box. That's going to be your geo heat pump. And then in this use, we're using this black tank here as our thermal storage tank. So the guts of the actual geo system is relatively simple. What can become a lot more complicated is on the hydronic end of things.
Yeah.
And then this is another sort of in progress picture of a hydronic system, kind of given a similar. So in this one, there's actually 2 geo heat pumps. The house was pretty massive, but the white box there is going to be one of the geo heat pumps serving the lower level, and then the silver box is the other geo systems serving the rest of the home. So you can get into multi-unit applications, and kind of everything in between.
So this next slide was quite a collaboration. So I had put together a slide based on 100,000 BTUs. What is the cost? That's a therm where we come from, 100,000 BTUs, but it's just kind of a normalization of some of the different heating technologies. So this is focused on heating, where electric resistance tends to be the big loser in New York, California, and Oregon. But we see that ground source heat pumps are the winner, at least by a little everywhere, if not more in some places. So the traditional business has been delivery fuels, so propane and oil, electric resistance. Those folks have been the best targets because they have the most savings. So you have good payback. We're finding now that we end up in natural gas areas frequently because of climate laws. The utilities in New York and other states are starting to look at moving away from natural gas and looking at alternatives. Network geothermal is one of those alternatives. And we do show some savings relative to that, but it's not as dramatic as it would be, say, if you had an oil furnace. The other thing that's always a little bedeviling, and when you go through something like this, is the efficiencies for these different technologies are really different. So the ground source system might have an efficiency that's 450%, arguably, or a COP, coefficient of performance, of 4.5. But that's not directly comparable to a gas furnace that might have an efficiency that's in 92% or even as high as 95%. Why wouldn't we really be much, much better? It's because they have different fuel sources. So efficiency is really only, so the electric technologies, which are electric resistance, air source heat pumps, and ground source heat pumps, those are a straight efficiency relationship with each other. The others, we really have to look at the fuel itself and then its efficiency. But this is a good way to just compare on cost. The efficiency numbers can be deceiving, but it's nice to do it regionally.
Yeah, maybe just jumping in on this, because I get into this a lot, and one of the deviling things about this is actually choosing what those efficiency numbers are for modeling. And the other thing is that these fuel costs are fluctuating constantly, so. But I think in general, what we see is both electricity and gas prices are going up. Which one's going up faster is a very regional difference, which is why I think it's helpful to see this in different parts of the country. And I know there are people out there who aren't from either New York, California, or Oregon, but Oregon is pretty close to the national average in terms of electricity and gas prices, but maybe on the low side on electricity. But you can see in states where electricity is expensive, that's one of the reasons why geothermal starts to really shine, because of its added efficiency.
Right, and it's a separate topic, but why? What are the when we deliver these fuels at the prices they're delivered at? How does that come together? Is that really a fair system? Some of these are regulated, some of these are not regulated. In New York, propane and oil are not regulated, for instance, but electricity and natural gas are. So there's all kinds of factors that feed into this.
Yeah, great.
I'll grab this. So on a incentive basis, we do still have for residential systems a 30% federal tax credit. That's an income tax credit. So you have to make some money and pay some taxes, but most folks do. So we find people can take advantage of that. You get that when you file your taxes after it's been installed. So you have to come up with the money somehow or find a short-term financing to make that effective for your installation. In
John,
New York,
can you carry that over 5 years like solar, or do you have to file for that all in 1 year?
The way the law is written, it says you can anything that you don't use, you can use the following year. But then when you get to that following year, I know a lot of people who have taken it the following year and the following year and the following year with no event. But right now, I think it's the safest to say in the federal tax credit that you have at least 2 years, and then it's up to interpretation. I've never seen anyone trip over taking it out over a longer period of time. The state incentive, we do have that for 5 years, that you can take your New York State. We do have an income tax credit that is specific to geothermal heat pumps, which is nice. That came into effect a few years ago, and we're looking to maybe expand the cap on that to $10,000. I have to say that's less valuable. Generally, people don't pay nearly as much New York State income tax, and so a lot of our lower income, middle income customers don't have that tax liability, and they really need it to be a way to lower their cost on installation. So if they can't take advantage of it quickly, it becomes a little less effective. We're trying to also put into legislation that it would be refundable, so you wouldn't need to have tax liability. So if we did that and we brought it up to 10,000, that would make that incentive really quite effective. Not applicable, I think, is what that is. So sorry, Oregon and California. But there are state incentives in a number of other states. We don't have an exhaustive list here. We also have rebate programs through our utilities. Con Edison is a utility, that's that second bullet, that has a rather significant program that can get up to $30,000 per residential install. The rest of the state, so that's the New York City area, Con Edison, the rest of the state is somewhere between $1,500 to $3,000 per ton or heating ton. And it's really 10,000 BTUs is actually how that system works. And you divide that by the heat pump capacity. That usually ends up being maybe in the 10% of the install. So it makes the needle move, certainly. So if you're in New York, you get that federal tax credit, you get that New York State tax credit, and then you also get a utility rebate. So the competitive pricing on electrifying with geothermal is much more competitive with air source in a state that has that level of incentive.
Hey, well, just on this topic, because I was digging a little bit here in Oregon, and obviously we have no utility incentives. Would include, in my book, things like oftentimes there's an efficiency organization that collects money from the utilities and disperses it in terms of incentives like Efficiency Maine, for example, Efficiency Vermont. Here it's Energy Trust of Oregon. All that's utility money in a sense that we pay as ratepayers. But I was surprised to find that there are a few states that have utility-based incentives for geothermal, whereas many of them, if not most of, a lot of them have them for air source. Do you have a sense of why it is that there's air source incentives but not geothermal incentives, when the systems you would think would be even more attractive from a kind of utility standpoint to put in geothermal rather than air source heat pumps? Why is it that that's the case? Is it just unfamiliarity, or what is it?
We thought that was so crazy in New York that we ended up getting them to make a rebate for us. So we're good. But yeah, I agree. I think there are very few installers of geothermal heat pump systems. That's a big challenge for us. We have, I think, maybe 500 contractors in the clean heat program in New York, but a very small fraction of those actually install geothermal systems. So more of I just think the mass market is currently still that air source heat pump market. It came out of if I could do an air conditioning system, I can install an air source heat pump. It's pretty quick. The ground source heat pump is a little less accessible. It requires another competency. You need to know something about the ground, or someone on the team does. And then there's a different set of equipment for it. So the HVAC contractors don't own excavators, they don't own drill rigs, and they're unfamiliar with site geology. So it's a little like one of the challenges the industry has is we're asking the designers and installers. It's a little, if we look at plumbing, it would be like having a plumber that does the internal work in a house design a septic system. They don't design a septic system. They hook into a septic system, but that septic system is really a separate thing. We have this outdoor component, which is always a little bit of an arm's distance, I think, from the mainstream market. And I think that's one of the interesting things about having the utilities or certain municipalities engage in this at a big scale, because it'll give us a way to normalize that really added difficult competency. If we could kind of centralize that, and then we can have, if let's say that there's a ground loop that's put in the streets, which is a separate webinar, then all we need to have, the internal HVAC contractor just needs to do the internal bits, and he hooks up to a couple of pipes that are stubbed through the wall like he does with natural gas.
Gotcha. Nick, are you seeing any kind of movement on this kind of incentive for geothermal here on the West Coast?
Yeah, I mean, I think we're trying our best, and I mean, I think the interest is really pushing things along as well. As everything becomes more and more electrified, the grid, you know, people who work with the grid or are aware of how it all really works are, you know, a little bit worried that, you know, capacity is going to be there. So there's some real interest from that standpoint. But I think as consumers become more aware of the systems, a lot of times that drives incentive as well. There's sort of a push-pull, if you will, related to that.
Yeah. Hey, while we're on this slide, one more question. Here's where we're going to put you guys on the spot for how much these things cost. So I know this is always a tough question because, you know, it's like, you know, how much does it cost to build a house? It's like, oh, what kind of house are you building? So I know there's some latitude that we need to give you on this, but can you just give us a kind of rough comparison? And maybe a good reference would be an air source heat pump system. And I know some of you guys have familiarity with both. Give us an idea about, you know, what a system like this would cost, what the incentives really make, you know, what kind of difference that makes in the end cost and how that might compare to an air source system. Can you just give us a general idea?
You're it, Nick.
I would say typically what we've found, and I mean, it's not exactly where the 30% rebate number came from, but you could, I think from a ballpark standpoint, you could say that after rebates, a geothermal system in a retrofit could be about 30% more expensive. I think that's, yeah, I mean, again, it's just like you said, there's a million different type of cars or houses or whatever. But I mean, I think if you were to just sort of ballpark it and say it's about 30% more expensive in a retrofit situation, I think that's relatively accurate. In new construction, I mean, you'd be very surprised, especially depending on the situation, how cost competitive you could be from the jump. You know, it's going to depend on the project, but you know, if you can be close in cost pre-tax credit, I mean, in new constructions where we really geothermal a lot of times is a real slam dunk.
John, what are you seeing in your area?
Yeah, we certainly have it's still a premium to do it. We have a 30% federal tax credit, New York State tax credit, and the utility rebate. We're still more expensive than, I would say, kind of an equivalent air source system. A lot of times air source systems don't do the whole house that our systems do. So you do get into that apples for apples comparison. We find that in propane and oil, you know, delivery fuel areas for homes, the paybacks are awesome because they have a big expense related to their operating costs that they can take down with the geothermal system. Against natural gas, we still cost, I don't know, we probably are still 10 or 20% more than the air source equivalent. The thing in natural gas areas that's interesting is that if you convert from a natural gas home to an air source heat pump home, you have negative savings. You're going to pay more in the natural gas goes away and the electricity will be greater, where a ground source system, you'll be cost neutral or some savings. So even though if we just take that little bit of savings and we say, okay, how long will it take to pay back that incremental extra cost? Still, that natural gas customer, you're out 20 years or something like that. But understand that that customer, if they go air source, has a negative bill impact from day one. And the cumulative impact of that needs to be considered too.
Yeah.
Gotcha.
Well, maybe we should round out our slides so we can get to some Q&A. This has been amazing. Is this, oh yeah. So
Yep.
Go ahead.
Next slide. Next slide.
Oh, next slide, sorry.
Yep. So this is from the New York Independent System Operator. These are the folks that control the electric grid in New York, and there's different systems like this in different parts of the country. And if you look on the left side, that's kind of today-ish. Is from 2021 data, and it shows the winter peak and the summer peak. The winter peak is that light-colored trace, and the summer peak, and you'll see that we're summer peaking right now. And that's true. That means that on the hottest summer day is when we use the most electricity. And on a winter day, it's quite a bit less. But then you see those, they cross over. And so with the electrification of buildings, with the electrification of automobiles, and now this new sources that are coming up with data centers, AI, crypto, those are all becoming bigger sources. We expect to see, but mostly because of buildings, we expect to see those curves cross over. Once we go to that winter peak, that's when we really start to make investments. Because right now you'll see that the summer peak is predicted to be somewhat flat in the New York area, New York State. But that added anything over that line, super expensive to build. There's a lot of money that it takes to do that. But that's based on mostly air source heat pumps. It's not based on a large proliferation of ground source heat pumps. And so what we often talk about is how do we value that avoided cost, and how do we get that avoided cost to help install the thermal infrastructure that will enable that curve to stay as flat for as long as possible. Next slide.
Yeah, and this is kind of exactly what John just touched on. This is, on the utility side, it's almost its own presentation. But I mean, the real push in a lot of ways is focused on these sort of peak events, and kind of like John described, imagine a 110-degree day and everyone's running air conditioning, the data centers are pumping, et cetera, all the electric cars are plugged in. This is where there becomes a real kind of concern about the stability of the grid and whether it can handle these peak events. And then what the research has showed and it continues to show is that ground source systems can play a real role in mitigating this moving forward. In the gas utility, this is another thing where I think it could easily be its own presentation. But the long and short is, loop ownership, financing, it can bring a whole new revenue stream for gas utilities. Dual fuel applications is a whole other thing, climate mandates, et cetera. But it's a really exciting kind of opportunity, I think, for utilities, because ground source has historically been pretty underutilized. But it's in their toolbox, if you will, kind of ready to go.
Hey, Nick, just on this one, because I'm very familiar with the pilots that are happening on the East Coast, and they're starting to happen here on the West Coast too, with thermal energy networks, where the gas utilities are actually some of the people that are implementing the systems. Is it fair? Is it true that there's a scenario where gas utilities might be doing these individual systems, or is it more really focused on thermal energy networks, this gas utility participation?
Oh, I think it's both. Certainly. I mean, in Oregon, there's some climate mandate stuff. We did a individual system pilot project with the gas utility this past summer. So I think there's definitely things happening. Thermal energy networks are sort of like the hot item right now. You're going to hear a lot about it. Individual systems, there's a lot going on. It's sort of the snowball is just getting going, if you will. But there's definitely things happening.
There are regulatory constraints that would keep the current regulated utilities from moving into individual system installations. Also, the federal tax credit doesn't favor individual building third-party ownership models. There's no eligibility for the tax credit unless you own both the ground loop and at least one heat pump. So there's some challenges with the utilities adopting a single building approach.
But John, the utility could, as you said, put a thermal network in the street and kind of.
That's correct.
Yeah.
Yep. And that's happening. We're involved in 7 or 8 of those projects right now.
Super exciting. Yeah.
Yeah, that's got to be another webinar. So I hope you guys are ready for a couple more. So, all right. Go ahead.
And then, community is another, the workforce side of things, a tremendous opportunity to bring people into the workforce. I kind of highlight schools. I think industry-wise, schools is kind of a low-hanging fruit. They tend to have pretty large footprints, which opens up opportunities for different kinds of ground heat exchangers. They're also big energy users. Less noise pollution, improved grid resiliency. And then from the consumer, and I'm conscious of the time here as well. You know, we call it hyper local. If you're an individual, I mean, you're literally the source of heat is, you know, your backyard or your property. There's, you know, lower utility bills. The longevity of the systems, I think, is often understated. When you get into, you know, cost effectiveness and cost comparatives, a lot of times people are not focusing at all on replacement costs. So if a system lasts twice as long and then that ground heat exchanger can last, you know, 10 times as long, is that really being accounted for when people are calculating payback? I think oftentimes it isn't. You can make an argument for improvement in air quality, and then there's some versatility to the technology as well. We didn't dive too far into domestic hot water, but that's another thing that geothermal systems can tackle as well. So it's able to be applicable in so many different scenarios. I think that makes it really versatile.
Great.
Yeah,
There
this
we
is
are.
fantastic. Thank you. And I know we've got a lot of questions here in the Q&A. We're probably not going to be able to get to them all, but let's try to pick off a few. Joe's, you want to, any that you
There are
jumping
58.
out to you?
Some of the questions I was sharing the screen.
We were either not, they're very
Okay.
curious, or we
Well,
were very unclear.
No, I think it's good. Some of these we've definitely answered. You know, one of the questions I had, which is maybe kind of buried in some of these questions, is are there things that are happening in the installation and, you know, maybe particularly in the ground loop side that are bringing the cost of these things down over time? You know, what kinds of trends are you seeing that potentially might reduce costs in the future of this technology?
So there's in Sweden, they probably have the most per capita installations. It's really quite common. It's amazing how many, the density of some of the installations. And as a result, they have a more mature industry. And that mature industry has some drilling contractors like Rototech that's come over to the US recently that has a very mechanized way that they conduct their business. And they have relatively small track rigs that they bring out. They've got dumpsters that they put materials into to make the cleanup easier. And it's really the set of procedures. Dandelion also went in that direction with their drilling technology when they came into the marketplace. So I think that it isn't necessarily, none of the things that they're doing are things that you might patent or that are incredibly innovative. It's really a way to just mechanize and have it be a repeatable process, because that ground loop can be a big extra expense, obviously, with our technology.
Is it fair to say that the ground loop, I mean, if you're comparing the two systems, you know, what the stuff in your house is roughly the same, it's the ground loop that's the added cost? Is that a fair summary?
That's the biggest component of it. Correct. Yeah. And I do think that we have installers that do air source heat pumps and that do air conditioning systems and furnaces. They might just not have the experience with the water side, the source side of it. It's really easy to learn. It's not particularly complex. But if we had someone take care of the ground loop, we definitely could get the majority of the heating and cooling contractors into the installation market. It's just right now the design and installation of the ground loop is still tied with the install in companies like Nix and mine. But again, that's one of the reasons why some of the utility efforts are so interesting right now, because they offer that sort of that third party takes care of that competency that the internal installers don't have.
And maybe a quick question I saw twice in our long list of questions. Can an air source heat pump ever either be the backup system or the primary system with the geothermal as a backup? Do you ever pair air source and geothermal systems together? Or does that not make sense?
We never have. I don't know, John, have you ever?
Yeah, I would say we have some buildings where they've done like an outbuilding or an addition is done in air source because it's just easier than expanding the geothermal system, and it might be a 3-season room. But for the most part, it isn't that there isn't an advantage to that. There are some systems that you could really cob together, that you'd basically say when it's temperate out, let's use that air system. And when we're in the extremes, let's use that ground system. It's just that you end up having kind of a unicorn of an install that is hard to service and have it be repeatable. It also, when you're doing the air source component, and the ground source component, then you've got both of those installation pieces. And it's a little hard to make the economics work. We did something similar. We did solar thermal and geothermal. So solar thermal would be the primary hot water system for domestic hot water. And then when it wasn't making hot water, it would help the geothermal system efficiency, it would help heat up the ground loop. It worked, but it was just a little bit too much of a science project. So generally speaking, installers try to stick with equipment and installation and maintenance techniques that they can scale broadly. So it isn't a good idea. It's just a little difficult to implement and service.
There's a couple of questions about seismic and earthquakes and maybe other variables like high water tables or something like that. Is that something that might preclude you from doing this?
Yeah. Hot rocks, where you're really getting into magma and you're getting into more sort of tectonic plates and things like that, that's where there's generally the geothermal gets tagged with a concern around earthquakes. The shallow work that we do, even if it's only a few hundred feet, I don't have any knowledge of a closed loop geothermal system that's used for a heat pump that had any negative seismic activity or did anything like that.
I mean, I guess it wouldn't be that different than a well, right? I mean, water wells are sometimes much deeper than that.
Even. That's right. Right.
So
much more common in that way. But
in the Northwest, I mean, we'll have the water table can, seep up to the ground essentially. I mean, there's areas of Washington where you only need to go down. You're into essentially the water table at only a few feet. So I mean, we're going to see, that's actually pretty common just across the river. The improvement, if you will, in thermal conductivity. But as far as, getting through vertical drilling through the water table, maybe is a different story. But I mean, it's really common in the Northwest, the groundwater, it's so shallow. It's just sort of part of the installation.
The water table has a pretty significant effect, or it can, on a horizontal system. And we tend to only install horizontal systems that have a soil type like a clay, or it has a lot of organics in it that'll maintain water, even if the water table drops. You can't really, and we'll have people say, well, we have it's sandy but it's always wet. And so if you put a ground loop in sand that you think is always wet, and then the water table drops and it's dry, now it's kind of like in popcorn and it doesn't perform well at all. So we tend to only put horizontals in if we think it's a soil type that will perhaps not completely dry out. So that's where the water table has a bigger effect, I think, on those horizontal systems than on the verticals.
Gotcha.
We are getting close to time. I think we still have so many questions that are not answered. I'm wondering if maybe we'll send you all 2 follow-ups, folks who are registered, one with the slides and recording, and then we will try to bother Nick and John a little bit to look at all the great unanswered questions there. There's some specific.
I have one. I just dying to ask Joe.
Okay.
So
Yeah.
I'm with you, but I just can't resist this one. So there's a question here about campuses, like college campuses. I know on the East Coast, it's really common. It's even common here on the West Coast to have these central boilers, and then, distributed energy systems. Like I know in Vermont, you'll have like maybe even a wood-fired boiler, and then you're sending steam all over the campus to heat buildings. Is there a situation? Is this kind of like a thermal energy network type of situation? But what about that application that is for geothermal? Is that a thing?
So there's two approaches. Smith College was a central plant, had a CHP, combined heat and power, that then distributed hot water and steam in places. And then they went to a central, or going to, it's still in process, to a central industrial sort of style heat pump that makes hot water and distributes it out throughout the campus, sometimes called a 4th generation system. It's more common that we'd have a 5th generation system which would be that we have boreholes or some other thermal source, and then we distribute through uninsulated pipes out to buildings, and those buildings have heat pumps in them. So more of a distributed effect. So, but I would say that campuses that have those central plants have the tendency to want to stay in that thinking. They don't have, some of the buildings don't have mechanical spaces, so they don't have anywhere, they don't really know where they're going to put the heat pumps in the building because they're used to having, say, that central steam system or that central chiller. And some of those campuses are using those more big industrial reversible chiller heat pumps and distributing hot and cold water out. But I would say more campuses are looking for ways to do an ambient temperature loop, which is basically an uninsulated pipe that we connect those borehole or other resources directly to buildings, and the buildings have the heat pumps in them and generate the hot and cold temperatures for the building.
Gotcha.
Great.
Well, this is great. We could probably ask you questions for a long time, so we should probably put a pin in this. We might send you a few questions as follow-up, but yeah, any last thoughts here before we wrap, Joe?
No, thanks so much, Nick. Thanks, John. Really appreciate your time and expertise. This is obviously a really popular topic, and we appreciate the work and coming on our webinar to help educate us all.
Yeah, and we'll be sending you know, a copy of the presentation and lots of links and other information out to all of you who've tuned in today. So thank you to our audience for showing up today and asking us all these great questions. And yeah, Nick, John, thanks very much. Super happy to have you here today.
Thanks for having us.
Thanks for having us.
Terrific.